So then, as said, the topic for today is network analysis, circuit simulation, circuit calculation. So we really start with electrical engineering now, right? What we have done before was just the prerequisite to do this. So we will take a look, a brief overview over circuit simulation, circuit calculation, network analysis methods. And then we will briefly discuss what we already did more or less. So what parts do we have in such a network? How can we describe the general structure? And then we will take a look at two methods. The first one is called branch current analysis and the second is called nodal analysis. And we will take a look at this using some example, some network and some circuit. And for this circuit, I've also prepared some experiment here. So I've brought a box with some resistors and a small breadboard and the multimeter. And so we can try to have an example that we can compare with calculation and measurement. Okay, so what do you know so far? What elements did we discuss in circuits? Capacitors, inductors, resistors, and sources, right? So we had resistance, capacitance, inductance, and also this mutual inductance. And this would be passive elements. And then we also talked about active elements, so ideal voltage sources, current sources. And then we described simple interconnects of this. So we've talked about basic electrical circuits and also Kirchhoff's voltage law, Kirchhoff's current law for meshes and for nodes. What rules, what other rules do you remember? Current and voltage divider. And what else? Ohm's law for resistors, and with Ohm's law and Kirchhoff's, let's say, voltage law, if you have two resistors in series and two resistors in parallel, you can calculate equivalent resistance. And so the Kirchhoff's voltage law, as said, tells us something about voltages, about currents, and then we have current and voltage at resistor, current and voltage at a capacitor, law of induction, current and voltage at some inductor, series and parallel connections, these current and voltage divider rules that you just mentioned, and let's say the basic electric circuit where we have one source, a couple of elements that are maybe connected in series and parallel. Okay, so this is, let's say, what we know so far. So then the question is, where have we been stuck? What is a problem that we cannot really solve, or that we could not really solve with what we know so far?
A second source at a different point?
A second source. So if we have two sources in a circuit, one source would push a current in one direction and another source would push a current in the opposite direction, and then we might have a resistor or a couple of resistors that are powered by two sources. So what is the influence of the one source? What is the influence of the other source? Okay, so if we have several sources in one circuit. And do you recall another example, a problem where it was quite challenging to find a solution? Remember this circuit here. So what is the total resistance of this circuit? If we would not have this resistor R5 here in the center that bridges this node and this node, then it would be fairly simple. We would have this resistor in series, and this resistor in series, and then these two branches, let's say, in parallel, and this would be the total equivalent resistance that could be measured at these terminals A and B. And if we would have a short circuit here, it would be also no problem, because this and this one, they would be in parallel. R2 and R4 here at the bottom, they would be in parallel, and then we would have the series connection of these two sub-circuits, let's say. But this one here really makes it hard to solve, because even if they look like they are in parallel, they are not in parallel, because there's not the same voltage across them. These ones here, they're also not in parallel, because there's not the same voltage across them. And this one and this one, even if they somehow look they are in series, they are not in series like them, because it's not the very same current that flows through them, because of this resistor R5 here in the center. And yeah, so this is also some not too complicated problem with, let's say, at the end maybe just one source, where we still need more advanced calculation methods to solve something like this. Okay, so we need calculation methods for the more general case, and this is, as already mentioned, more than one source or more complicated interconnections like we have seen in the example. Okay, so then the question is how to do it. And there are lots of methods, and so the one that we will look at today, and yeah, maybe the more, not, yeah, it's always difficult to say what is the simplest one, but let's say this is the most straightforward one. Branch current analysis is, as we will see, we just set up Kirchhoff's voltage laws, Kirchhoff's current laws. We insert, let's say, Ohm's law if we have a circuit with resistors, and then we get a system of equations and we try to solve the system of equations. Okay, so that's this. So then the disadvantage here is you get quite a high number of equations and unknowns because you set up all the Kirchhoff's voltage laws, all the Kirchhoff's current laws. So there's a second method, which is called mesh current analysis, where you just set up Kirchhoff's voltage laws in a special way so that, let's say, that the current laws will be directly included there. So you get an equation system with less unknowns. That's the idea here. And if you have less unknowns, it's easier to solve, at least if you solve it by hand. And yeah, maybe as the saying is, where light there is shadow, there is no free lunch, as the Americans say. So there must be some disadvantage here, because otherwise if this would only have advantages, no one would use the first one anymore. And the disadvantage here is that you at first you only calculate these mesh currents, and the mesh currents are not really measurable currents. It's just, let's say, auxiliary quantities that are helpful for the calculation. But from these mesh currents, you would have to calculate your real branch currents. And so there's another method that is quite similar, which is called nodal voltage analysis. This is also the one that we will talk about today. And this is only based on Kirchhoff's current laws at first. So you just set up equations for all the nodes. And then the voltage laws are also somehow included there. So we also end up, in comparison with the first one here, we end up with some equation system or system of equations that is smaller, has less unknowns, and is easier to solve, therefore. And there's also some other advantage here that we will see later on. And that's why if you use LT-Spice, if you use Easy EDA, if you use almost any circuit simulator out there, some circuit simulation software, what they will do in the background is always this nodal voltage analysis. And a more general form that is called modified nodal analysis, or short MNA. And so, yeah, but this is the method that is based, or that is used in many softwares, or where many softwares are based on. Okay, so another method is called superposition. The idea of superposition is, okay, if it's a problem, if we have more than one source, just let us look at each source separately. Switch on one source, check what is the influence on the circuit, switch it off once again, switch on the second source, check what is the influence on the circuit, and then combine at the end everything together. This is called superposition. And so then there's another method that is based on based on many theorems. In German it's quite simple. It's just called Zweipol-Theorie, so two-pole theory, let's say. But in the English literature there are many different names for this: Thevenot's theorem, Norton's theorem, Millman's theorem, and it's all about circuits with one port, and one port means you have two terminals, like here, like in my example. Yeah. This would be also a one-port circuit, because the same current that goes in also needs to go out. No current can can disappear somewhere. And this is called a port condition, and all these theorems are about active one-ports, active circuits that have two terminals, and how you can combine them and how you can simplify them. And so you try to express your circuit at these one ports, and you try to combine them with each other. Okay, and if you can do it for circuits that have one port, then the next step is you could also do it for two ports, for circuits that have an input and an output, or that have an input and two outputs, something like this. So this is called two-port theory, and you could extend it to n ports and could write down similar parameters like these ones here for the two ports. And so a passive one port, like a resistor, or like our circuit here that we had, this interconnection of resistors, at the end, this would be one parameter. We could combine all these resistors. If we are just interested in what is the behavior at these terminals, we can combine the whole circuit into one parameter, into this equivalent resistance. And if there would be a source in here, we would need to have two parameters, like open circuit voltage and inner resistance, or short circuit current and inner resistance. So you would need two parameters. And for these two-port networks, you need 2 by 2 parameters. So you need a matrix with 4 parameters. And for n ports, you need n times n parameters. And you can always write them down in a matrix form. Yeah, but okay. This is just a very brief idea. And a last method that can be used is using graphical methods. If you have circuits with nonlinear elements, then it's always really challenging to calculate something, but still you can try to draw something. If you have a circuit, remember when we measured the characteristic of the diode, yeah, that was this exponential function or logarithmic function. You can always try to find some operating point of a circuit by drawing this characteristic of the diode and trying to find the intersection with some source or with something else, just in a graphical way. Okay, so then let's talk about network structure. And so we just need to have some terms and definitions that we are all talking about the same stuff. So a resistor is a component, for example. A capacitor is an inductor. These are all components, and these are devices with two terminals. And if we would have a transistor, for example, this would have 3 terminals. If you have some transformer, this would have 4 terminals, 2 at the input, 2 at the output. But let's say this is a component. Okay. And the point where different components are connected to each other, this is called a node. And at this node, Kirchhoff's current law applies. And yeah, so this is the usual, let's say, standard teaching book, textbook definition or Wikipedia definition, that there are more than 2 components are joined. Still, sometimes it's useful to have, let's say, to have a fake node somewhere in a circuit where just 2 components are connected to each other. And I mean, still, then Kirchhoff's current law applies, but the input current is the same as the output current in this fake node, in a node that is not really a node. So where current does not split up or current does not get combined, but just input current is output current. Then we have branches. Branches are things that connect nodes, and a branch must contain at least 1 component, but could contain also 2 or 3 or whatever components in a series connection. Okay, and so then if we walk along branches and if we do a closed loop, a closed circuit inside a network, then this is called a mesh. And inside this mesh, the Kirchhoff's voltage law applies. Right? And translated back into German, this would be Knoten and this would be Masche. And I mean, in German we say Maschensatz for the Kirchhoff's voltage law, and we say Knotensatz for the Kirchhoff's current law, because they apply to nodes and to meshes. Okay, and so then what, I think this is what we have used before. This is what should not surprise you too much. And what we need for today, and in the more general case, is called a graph. And a graph is a just simplified graphical representation of the network. Let's say just the structure of the network, but without the components. And we will see an example in a second. So all branches or nodes, but no components. And inside this graph, then we can, of course, more easily, we can also find it in a network, but in a graph it's more obvious how many nodes are there in the circuit, and we number the nodes with k, or the total number of nodes is k, and the number of branches where we want to know the branch current, or where the branch current is an unknown that we want to calculate, these we number with z. So our network has k nodes and z branches with unknown currents. Unknown branch currents. Okay, and so if we go back to our example, this was our example where we want to know the equivalent resistance. Okay, we need something to power this network, so we take one source. And if we would be able to calculate this current I6 here, then the source voltage divided by this total current, this would be the equivalent resistance of the circuit. And so this is our network, our example that we still have, and this would be the graph of this. So just the 4 nodes that I've somehow labeled here, and the connections, the branches, but without any components. Okay, and so yeah, from this graph we can find there are 4 nodes, so k is 4, and they are also 1, 2, 3, 4. If I count here 1, 2, 3, 4, 5, 6 branches with unknown currents. Right? 1, 2, 3, 4, 5, and 6. We also here it's not a current source, it's a voltage source. So this current is also an unknown quantity. Okay. So yeah, we have a network, we have simplified it to a graph, and our network has 4 nodes and 6 branches. Okay, so then we can try to start with this branch current analysis. And the prerequisite there, or let's say the prerequisite for all these circuit simulation network analysis methods is we have a network with active and passive elements, and we know all the values of these components, we know all the resistors, we know all the voltage and current sources, and we know the network structure, of course. So we know the network. And we want to calculate all the currents and all the voltages inside the network. And sometimes, okay, sometimes we maybe only want to have the currents, sometimes we maybe only want to have the voltages, sometimes we may only want to know a single current inside the network. Like for our problem, if we want to know equivalent resistance, we only need to find the total current at the end. But in a general case, let's say we want to find all currents, all voltages inside the network, they need to be calculated. Okay, so yeah, what is the procedure then? As said, we set up a system of equations, and this system of equations is formed from Kirchhoff's current law, or voltage law, Kirchhoff's current law, and the voltage-current relationships at the network elements like Ohm's law. And yeah, so in all the examples, we will stick to circuits that have just resistors and sources. So no capacitors, no inductors, because this would make things complicated. This we will do, what we will do later on just for AC. And in the final week of the semester, at the end of January, we'll come back to one problem where we take a network with, let's say, maybe a capacitor and a resistor and try to solve this in the general way. But you can imagine if your voltage-current relationship, like in the law of induction, includes the voltage is proportional to the time derivative of the current, then you get you get a system of equations of differential equations, and then it's really, really hard to solve. So we will stick to resistive circuits just to get the idea how this works. Okay, so we take our basic laws that we already know, we form a system of equations or a set of equations. And if we do so, then usually, as we discussed before, the number of equations that we can get from Kirchhoff's current and voltage laws will be larger as the number of unknowns. So we get an equation system with more equations than unknowns, which is not really bad, but also not really good. Usually we want to have the same number of equations as unknowns, and then we get a nice equation system that we can somehow solve. Okay, so the question is, how do we set up an equation system that has the right number of equations for the right number of unknowns, and where all the, so yeah, what is the next condition? Even if we have an equation system that has the right number of equations as unknowns, what condition do the equations need to fulfill so that we can solve this system of equations? So if I write down a simple example and say x plus y is, let's say, 3. And if I write down 2x plus 2y equals 6, I have an equation. I've written down an equation system with 2 equations and 2 unknowns. Still, can you solve this equation system? No? Why not? Because it's the second equation does not contain any new information. It's the very first equation just multiplied by a factor of 2. So we have a set of equations, but they are not independent of each other. So we need to have independent equations. That's the important thing. So the question is how to find independent equations and how to find what is called essential nodes and essential branches. So what Kirchhoff's current laws and Kirchhoff's voltage laws do we need to write down to get independent equation in our system of equations? That's the question. So how to find them and how to find independent nodes and independent Kirchhoff's current laws is quite simple. If we have k nodes, we always have k minus 1 independent nodes. It's fairly easy to show this. But yeah, just take it as it is, let's say. Well, you could show for some example that this works. So if we have 4 nodes in our circuit, we have 3 independent Kirchhoff's current laws that we can write down. Okay, so next question is how to find independent meshes and essential current Kirchhoff's voltage laws. And this is more complicated. So, and there's one method that is called, and to be honest, I've not really found this term in the Wikipedia or in English textbooks. It's more a direct translation of what we have in our German book. We call it a complete tree. And so this complete tree inside this network graph it's a segment, it's a subset of this graph, and it's a connection of all nodes without having a closed loop. And if you do in this network graph have a connection of all the nodes without forming a loop, then this is called a complete tree, and this always consists of k minus 1 branches. So yeah, we can take a look at the example in a second. And so then once we have this complete tree, then we can close this tree over the remaining branches, and each closing via some remaining branch, this will give us some independent equation, some essential Kirchhoff's voltage law. So remember, this was our graph. So one example for the complete tree would be, this is a connection here of all 4 nodes without having a closed loop somewhere. And so now we could close this tree over this branch. This would give us one independent Kirchhoff's voltage law. We could close it over this branch here, and this would give us a second independent Kirchhoff's voltage law, and we could close it over this branch. This would give us a third independent Kirchhoff's voltage law. So now we can calculate and say, okay, we had 4 nodes. This means we have 3 independent KCLs, and we have this complete tree. We have these 3 remaining branches, so we also get 3 Kirchhoff's voltage laws that are independent of each other. So yeah, one question that could be discussed for this example, how many of these complete trees exist? Just guess some number, because you could find other options that would connect all 4 nodes with each other without forming a complete loop. And yeah, and so if there's more than one solution, then it's always the challenge how to efficiently find one. And so even for this very simple example, there are already 16 different variants. And this is at the end the problem. If you have complicated circuits, it will be quite complicated to find such a complete tree. But you need to have something like this to find independent meshes to get an equation system that you can solve. And so this is the reason why this branch current analysis or mesh current analysis is not really used in circuit simulators, because it's hard to program something like this to find complete trees in circuits, in networks. Okay, so going back to our example, we can now try to set up some equation system, and I will copy this and copy it to my drawing program. Right, so here I can delete this example once again, insert our circuit. And so then we can maybe start with some Kirchhoff's current laws. And so for the node A, it would be
I6 equals I1 plus I3.
So I6, I will, yeah, and maybe I will, you're completely right, but I will just write it in a different order.
Plus I1 plus I3 or
Yeah, something like this. So I would say things that are flowing away from the node, I will count negative. At the end, it does not really matter. So minus I1 minus I3 plus I6 equals 0. Exactly. So then for node B, that is this one here. We have plus I2, right, plus I4, and minus I6 in this case, and this is also 0. And so if we do it for the last one, for example, for C, then in this case, plus I1 plus I5 minus I2, so I1 plus minus I2 plus I5 equals 0. And so just as a short check, I will do it in gray. If we would add up all this, so minus I1 plus I1 gives 0. I2 minus I2 gives 0. I3, we only have one I3 here, so let's note down one I3. So then we have I4. This is also what we have just once, plus I4. I5 we also have just once, plus I5, and I6 plus and minus, they will once again cancel each other. So what we get here is exactly the Kirchhoff's current law at this node, but just with the opposite sign. Let's say this is minus D. This is flowing into the node, and these two are flowing out of the node. Yeah, so this would be some dependent equation, would not give us any new information. If you have k nodes, you have k minus 1 independent Kirchhoff's current laws. Okay, so with a different color, I will write down Kirchhoff's voltage laws. And so we said, okay, this is our first, or could be our first independent mesh. This could be our second independent mesh. And this could be our third independent mesh. So for the first one, what can I write down? If we, yeah?
The source equals V1 plus V2.
Exactly. So the source voltage would be this voltage plus this voltage, and this voltage I will express in terms of the current. So I will say this is R1 times I1 plus R2 times I2, and this should be the same as the source voltage. So for the second mesh, if we start here, we have plus R3 or plus U3 plus U5 minus U1 equals 0. So R3 times I3 plus R5 times I5 minus R1 times I1 equals 0. And so for the last mesh, it's maybe if we start here, it's yeah, or I will at least try to write them in the right order. So minus R2 times I2. This is plus R4 I4. You will check that I'm doing not a mistake, right? Okay. and this should be minus once again. So minus R5 I5 is also 0. Okay, and so now we can, you could also check if we would, for example, take the sum of all three. We can do it once again. If we take the sum of these three, so this and this would cancel. This and this would cancel. R3 we only have once, so we would get R3 times I3. So the R4 we also have just once. And the R5 would cancel each other. And on the other side, we just have V source. And so what mesh equation have we written down now? It would be the outer loop. So this would be like the outer loop around the circle. And once again, around the circuit. So once again, this does not include any new information. It would be also some dependent equation that depends on the ones that we had before. Okay, so but until there, we have 1, 2, 3, 4, 5, 6 equations, and we have 6 unknowns. So it's a nice equation system that should be possible to solve. Okay, so yeah, the next step maybe would be to write down this equation system in matrix form. So I can try to do this here very small on this side here. So here we have all the coefficients. Here we have our unknowns. And here we have the known sources. And so if we start, yeah, so this is the for I1, I2, I3, I4, I5, and I6. Yeah, so these are the unknowns that we want to calculate. And we can check. So here we have -1. I will just write all the other coefficients that are not right down are 0. Here's -1 and here is a 1. So in the second equation we have 1, 1 and -1. In this equation we have 1, -1 and a 1 here at this position. And so the result in this case is always 0. And so maybe I should have used green for this, so these, or blue for this. These are the KCLs, the Kirchhoff's current laws, and now we continue with the Kirchhoff's voltage laws. And so we have here R1, R2, and our source voltage. And here we have R3, R5 and minus R1, and in the last one we have R3, no, wrong, minus R2, plus R4 and minus R5. And the result here will be also 0 in each case. Okay, so now we have this equation system in a nice compact matrix form. Now next step would be to solve this, of course, we do not solve it by hand, we solve it with MATLAB. So you can scan the QR code, you can also just throw in numbers into the room. How many systems of equations have you already solved with MATLAB? I can maybe also open this up in my browser. If someone wants to scan the link, so can I get this on the same page here? Yeah. Okay, we have one answer for none so far. A second answer for none so far. A third answer. Did you know that there was a mathematics preparatory class before the semester? I'm not sure if in the English one, at least in the German one, we also do it there with some simple example. Okay. Okay. Yeah, so let's do it. So there is Octave here. I will also try to move this to this side and yeah, find my matrix equation system there. So we need to insert this matrix, and I will call this matrix, which is not a super intelligent name, but it's okay. So there's -1, so then I need a 0, there's -1, 0, 0, and a 1. With this semicolon, I can go to the next row, and there I have 0, 1, 0, 1, 0, -1. In the next row, I have 1, -1, 0, 0, 1, 0. In the next one, oh, okay, so now I have R1, and we need to have values. So I will write down at first R1 and R2. So MATLAB will throw up, or Octave will throw up some error message, then we will give them values. So then we have minus R1, then we have 0, R3, 0, R5, and another 0, and then we have 0, minus R2, 0, R4, minus R5, and another 0. And this should be our matrix, and then, okay, it says R1 is undefined. So we need to have some values, and the values have been given here in my example at the beginning. Hopefully somewhere. So here are the values. 1 kilo ohm, 2 kilo ohm, 1 kilo ohm, 1 kilo ohm, and 3 kilo ohm. So R1 is 1 kilo, R2 is 2 kilo. R3 is another 1 kilo, R4 is another 1 kilo, and R5 is 3 kilo ohms. Right? This should fit to what was just written there. Okay, so then I can go back to this matrix thing, and there should be the matrix. So let's do a quick check if this somehow works. First line does not look too bad, second line does not look too bad, third line also does look good, fourth, fifth, sixth line do look okay. And so the voltage source, I will just set it to 1 volt. Okay, so now the question is, how can we solve this equation system? So at first we need to have, let's say, the right side of our equation system. And there is 0, 0, 0. Then we have the source voltage. Then we have another 2 zeros. So this will be the column vector. And yeah, so let's say the most obvious way would be to say we have this matrix, which is multiplied with our vector of unknowns. And here we have this known right side. So if we take the inverse of this matrix and multiply the inverse of this matrix from the left side, then inverse matrix times matrix gives the identity matrix, and the identity matrix times the vector gives the vector. So here we get our vector, and on the other side we have the inverse of this matrix multiplied with this source vector. So we get our currents from the inverse of this matrix multiplied with the right side vector. Yeah, the names here for the variables are not super intelligent, but it should be understandable. And so now we get the 6 currents. And so as we said, from the last current and the source, I should get the total resistance. And so for the total resistance, if we have, yeah, what would we expect if we do a rough approximation? So we have, let me go back to the example. So we have 1 kilo ohm and 2 kilo ohms. Let's neglect this R5, right? So we have 1 and 2 in series is 3, and we have 1 and 1 in series is 2. And so then we have 2 and 3 in parallel. So how do we calculate this?
1 over 3 plus 1 over 2 is 5 over 6, so 6 over 5.
6 over 5, or 2 multiplied with 3 divided by 2 plus 3. So 6 over 5. This is 1.2 kilo ohms. And so now if we insert this R5, what should happen? Nah, I would say it should decrease, because we allow some current that would need to go over the 2 kilo ohm resistor. We would allow this current to go over the smaller 1 kilo ohm resistor. So the total resistance should get smaller, slightly. Okay, so yeah, let's check our wanted resistance that we want to have. The equivalent resistance RAB is the source voltage divided by this last current. And the last current is the 6th current out of this vector. And so when we see, okay, we get 1000, not 1200, but 1190.5 ohm, which sounds not too bad. It's the right, correct answer for this problem. Okay, so we get slightly less than 1.2 kilo ohms in this case. Without the R5 resistor, we would get exactly 1.2 kilo ohm. Okay, so we have successfully applied branch current analysis all this way here with the graph and the network, and writing down and solving the equation system. So what we could do now is to do a small experiment, as already suggested, and compare it with some measured equivalent resistance. And so there's my camera window, and I will maybe try to make this a little larger. Or maybe I can also go to full screen mode. I'm not sure. Yeah, this does not look too bad. Okay, so there's my full screen camera window. And so I have a box, and inside this box, because I transported this with my bicycle, everything shifted a little bit, but here, as you can see, this is the box with 1 kilo ohm resistors. So we have 1 kilo ohm resistors. This is the box that somehow says 2 kilo ohm. This is the 2 kilo ohm resistors. And then I have a last box that says 3 kilo ohm resistors. So this is the 3 kilo ohm resistor box. And then I have a small breadboard where I can try to build a circuit. And I have my multimeter here that I can set to measure resistance, and I have 2 measurement cables that luckily have clamps. So I will take a 1 kilo ohm resistor from this box and already place it on the breadboard here, and measure this resistance. So you can see it's, as usual, not exactly 1 kilo ohm, something slightly less. Okay, but we could try to remember this value. So then I take a resistor from the 2 kilo ohm box and measure this separately. So this one, as you can see, has slightly more than 2 kilo ohms. Okay, so if I put them both in series, the total resistance that we should get should be something like 3 kilo ohms. Okay, so this works. All right, let me take a picture of this. Okay, so then this is the left side of the circuit. So then we can take the right side of the circuit. So I have another 1 kilo ohm resistor. I can measure, this has less tolerance. This is very close to 1 kilo ohm. And I have another 1 kilo ohm resistor that I will measure separately. Yeah, so this has more tolerance. This is less than 1 kilo ohm, but okay, it's for our purposes still usable. And so if I connect these two in series, for the right side of this network, I should get something like 2 kilo ohms. So this somehow works. Okay, so then I need some cables to some short circuits to connect the top nodes with each other. And they are super difficult to push in, so I will use something that does not look this nice but does the same purpose. So one short circuit at the top and one short circuit at the bottom. And so now if I measure the resistance, we get 1.2 kilo ohms, slightly less because the right side, remember, had little less than 2 kilo ohms. So now the last thing is, if we, let me take a picture of this. So last thing is, if we take a 3 kilo ohm resistor out of the 3 kilo ohm box, and now if I try to put this in the center, and remember this was the value, now it should get smaller. So if we put this in the center, and it does, and it decreased by approximately 10 ohm, like in our calculation. So yeah, this nicely fits. And perfectly matches to what we just calculated from this calculation and our solution in Octave here. Okay. Questions so far? Excellent. So then we can continue, and we still have like half an hour left, which should be perfectly fine, to take a quick look at nodal analysis. And so the idea there, and this is also some method that is like a recipe, right? You can, like if you bake some cake, you need to have the recipe, and then you can somehow apply this to a circuit. So yeah, and the Lactobacillum has written in the chat, your stream is lagging very much, like 1 frames per second. It should, I think it should get better now. Once again, I think it's because of the second camera. My laptop here, unfortunately, is not too powerful. But yeah, thanks for the comment. Okay, so if we want to do this nodal voltage analysis, and we will do it in a second also for our example here, we define a reference node. And by defining a reference node, let's say we throw away one node. Because remember, if we had k nodes, we had k minus 1 independent nodal equations. So the reference node is the one that is thrown away, the dependent one. And then we introduce nodal voltages for the other nodes. What this means we will see in a second. But it's always the voltage from each node with respect to this reference node. So then we express the branch voltages and branch currents in terms of these node voltages or nodal voltages. And by doing so, it's better to use the conductance instead of the resistance. It's just shorter to write it down, because every time you would write, you need to write 1 over R, 1 over R, 1 over R, and so on. So it's easier to write G for the conductance. So then we set up the node equations, except the reference node. I said this is the dependent one, so we get a system of equations, and then we solve the system of equations as before and calculate these nodal voltages. And from these nodal voltages, you could calculate all branch voltages, and from the branch voltages, you can calculate the unknown branch currents. That's the idea. Okay, so once again, we will take a look at our example. And in our example here, I have also at first removed the resistance R5. And I replaced the voltage source by a current source, because this current source is easier to use in nodal voltage analysis. It's more challenging to use voltage sources. So current source is easier here. So this is our example. So what was the first step? Have a reference node. So we will use this one here as a reference node, and we will somehow number the other nodes. Let's say this is node 1, this is node 2, this is node 3. So the next step, if you remember, was setting up these or drawing in these nodal voltages, and the nodal voltages are the voltages from each node to the reference node, to this ground node. And I mean, by the way, if you do a circuit simulation in EasyEDA, in LT-Spice, in any circuit simulator, you always need to set up a ground node, and the ground node is this reference node for the nodal voltage analysis. So we could also say this is ground. This is our reference potential. So we have, if we have 3 remaining nodes, we have 3 nodal voltages. The voltage U10 that goes from 1 to 0, second voltage, third voltage. Okay, so yeah, then we set up a system of equations. And so this is what I will once again maybe do and show in the other program, because then it's, I think, easier to understand and easier to follow. So let's have a new page here, or a new node, and maybe make this a little smaller. So the idea, as said, was to start once again with Kirchhoff's current laws. And so we can set up one for the first node, for the second node, for the third node. So for the first node, yeah, we would need to have directions. So let's say this is the direction here is always pointing downwards. So for the first node, we could say
I1 plus I3 is I source.
yes, or I will say minus I1 minus I3 plus I1, yeah, and yeah, and so difficult to say minus I source, but I want to have the source on the other side.
3 plus I1 is I source.
Yeah, so maybe I will just write like this. So okay, yeah, the source voltage is this voltage. Okay, the source current is the same as the sum of these two currents. And at the second node and at the third node, this is what I mentioned before. This is not really a node. It's like this fake node. But still here we can say that the first current minus the second current equals 0. And here the third current minus the fourth current also equals 0. Okay, so we have written down Kirchhoff's current laws. We have 3 equations, but we have, as you can see, we have 4 unknowns, unfortunately. So we can go back to like our recipe here, and the recipe says we should express the branch voltages and branch currents in terms of this node voltages. So if at first we express these in terms of the voltages, the branch voltages, right? This would be these voltages here. So then we would get, so I will use a new color. So now we, instead of currents, we write voltages. So from our first equation we get R1 times, no, not R1, G1 times U1 plus G3 times U3. This is meant by conductances are better than resistance, because otherwise we would always have 1 over R1, 1 over R3 and so on. So here we still have the source current. So for the second equation we have G1 times U1 minus G2 U2 equals 0, and for the third node we have G3 times U3 minus G4 minus, no, not minus, multiplied with U4 equals 0. Okay, still 3 equations for unknowns. Okay, so but now we, this would here be our branch voltages. Now we express the branch voltages by the node or the nodal voltages. And so let's have a second thing here. So if I want to express U1, U2, U3 and U4 in terms of nodal voltages. So here it's fairly simple. The last one, this voltage, this branch voltage is the same as this node voltage. So here I can say, okay, this is U30. So for this one it's also fairly simple. It's U20. So how can I express this voltage here in terms of nodal voltages only? Exactly. So the difference of these two, this one minus this one, must be this one. And so here it's the same. This one minus this one should give us this one. So this is also U10 minus U30. And so now we take this and insert this here into this equation. So we get G1 multiplied with U10 minus U20 plus G3 multiplied with U10 minus U30. And this equals the source current. So for the second node and for the third node, I can also write this down. G1 times U10 minus U20 minus G2 multiplied with U20 equals 0. And for the last voltage is G3 times U10 minus U30 minus G4 multiplied with U30 equals 0. And so now what we've got is an equation system, or a system of equations with 3 equations and 3 unknowns, namely the 3 nodal voltages. So this should be solvable. And yeah, so now I need to check if I can try to get this onto the, no, I think we have to do it in comparison like this. So now we can set this up once again as some matrix system. And so let's check. So here's our source current. Here are the 3 unknown nodal voltages. And so if we check in the first equation, so for U10 we have, this was G1, so we have G1 plus G3, G1 plus G3. So then we have minus G1 and minus G3 for the other terms. So minus G1 minus G3. Perfectly makes sense. So for the next one we have just G1, but yeah, okay, just G1, but here I have it negative, but it's no problem. I could just say, okay, I want to have minus here, then I get plus here. So minus and minus is also plus G1 plus G2. This is what we have here, and 0 and gives 0. Okay, and so probably for the last one I need to do the same. So have a minus here and turn this into a plus. So I have minus G3 times U1, 0, and then G3 plus G4. And this is what we have here, minus G3. Okay, so now if I now I think I need to go out of this and try to make this a little smaller. So if you take a look at this system of equations and at the very same time try to take a look at our original circuit, what do you see? So if we take a look at whatever is written here on the main diagonal of this matrix. So at the first node, we have the two components that are connected are R1 and R3. So here we have G1 plus G3. At the second node, we have connected 1 and 2. So here we have 1 and 2. At the third node, what we have connected is 3 and 4. So we have 3 and 4. So on the main diagonal, we always just have the sum of the conductances of the resistors that are connected at each node. Very, very simple way to set up this equation system. So usually you don't need to go this long way here. You just take a look at the circuit and you write down the system of equations. And this is also what LT-SPICE does, what Easy EDA does. It's so simple, a chimp could do it, let's say, almost. But it's very simple to program. So, okay, then we have the off-diagonal elements. And so here we have the first row and the second column. Or we have the second row and the first column. And we have the very same element. And this is the element that is connected between 1 and 2. And so here we have first column, third row, first row, third column. So here we have the element that is connected between 1 and 3. We have nothing between 2 and 3, or not yet. Yeah, that's why we have a 0 here. And these two, they do not count, let's say, because they are connected to the reference node. There is no zeros line and no zeros column in this matrix, and that's why they do not appear as an off-diagonal element. So each resistor, each conductance can appear once in this matrix if it's connected to the reference node, like G2 and G4, they just appear once. And the other resistors or conductances that are not connected to a reference node, they appear 4 times. 2 times on the main diagonal and 2 times on the off-diagonal elements. And so you also have ways to check the matrix. If a resistor appears 3 times or 5 times or 2 times, then it's wrong. A resistor can just appear 1 time or 4 times. And here we have the sources. So we have a nice system of equations. We can insert the values of our components, convert them into conductances, and put them into the matrix. And then the matrix looks like this. And then we can once again calculate our nodal voltages in MATLAB or in Octave. And so I will maybe do it like this. And go back to Octave and try to make the window fit on my screen. I cannot make it any smaller, but okay. So G1 is 1 over R1. and G2 is 1 over R2, and G3 is 1 over R3, and G4 is 1 over R4. And the source current is 1 ampere, maybe once again. So now we get a new matrix, and I will call this nodal matrix. And so this nodal matrix is G1 plus G3, then minus G1 and minus G3. So in the second row we have G1 but minus, exactly. So then we have G1 plus G2 and 0. And in the last row we have minus G3, then 0 and G3 plus G4. So we should get something like this. We can check with the values here. This does not look too bad. Okay, and then we have the source vector. And in the source vector we have 1, 0 and 0. Directly written the 1 in there. Okay, so then we can solve this as we did before and get our nodal voltages, or you might call them, it's always this challenge. So once again, the inverse of this, I think I've called this nodal matrix, and then multiplied with our source vector for the current. And so we get 3 nodal voltages out of this. And yeah, of course, we had resistors in the kilo ohm range. If we feed 1 ampere of current, we get kilovolts of voltage, which perfectly makes sense. So yeah, but then the remaining question is, so now we have this solution in MATLAB, and yeah, so how in this case, how we would get our resistance RAB? Yeah, U10 divided by the source current. The total voltage divided by our source current. Okay, and so we need to now have the first of these voltages. So RAB, once again, is the first of these voltages. So they were called V nodal, and then the first one, and then divided by our 1 ampere of source current. And so we get 1200, now not volt, but ohm, 1.2 kilo ohm, which perfectly makes sense. What we have also measured in the experiment. Okay, so solution in MATLAB or Octave, comparison with the measured equivalent resistance. This is what we have already done. So now we are still missing this bridge resistor there, the R5. And so now we can go back to our equation system, and now this is the charm, this is the big advantage, this is the glory of this nodal voltage analysis. It's very easy to additionally add this resistor. If we would do branch current analysis or whatever else, we would need to set up a new branch, and we would the whole equation system would change because we would have some additional unknowns, so we would get one voltage, one equation more. So you say, okay, and there are cases where this does not work, but in this case it works. We just have another resistor that connects this node 2 and 3. So what changes in our system of equations is we get plus G5 at this position, we get plus G5 at this position, and we get minus and minus G5 at these 2 positions. And everything else stays the same. And so we can insert the same values as before. We can insert them into this matrix system, and we can calculate it. And then we get our unknown nodal voltages. And so this is what I will do in Octave now. And so at first, I think, otherwise I will get some error message. I will need to calculate G5 from 1 over R5. And then this was the nodal matrix. I will move this up a bit. So this was the nodal matrix, and now I will call it nodal matrix nu, which once again is not a super bright variable name for sure, but it should work in this case. And so now we can check this 0, this should turn into minus G5. And this 0 here, this should also turn into minus G5. And then at the second and third node, so where G1 and G2 or R1 and R2 have been connected, there it's added. This should be some uppercase G, and so also at the last node we need to have plus G5. So this is the new matrix. Yeah, and I think this is similar to what we have written here. So the source vector is the same. So we could calculate our new nodal voltages from the new matrix multiplied with this vector, and we get correspondingly new nodal voltages. And once again, if we would calculate our RAB new first nodal voltage divided by 1 ampere current, you can already see the result. Oops, yeah, so new. Okay, yeah. So then we get the same what we had before. Yeah. So this perfectly makes sense. Here there was the old result that we had before from our branch current analysis, and this is what we had here from the nodal voltage analysis. So our solution in MATLAB works, and then I have two last, yeah, let's say questions for you. Two quizzes. So the matrix that we get, this nodal conductance matrix for the nodal voltage analysis, is it always square? Is it always invertible? Or is it always symmetrical to the main diagonal? Or are more of these answers correct? And so I think I will just once again click to this link. And there it should open up in my browser, and I will go to the results, and then you can cast your vote, whatever you think is correct in this case. So there we have some answers already. Okay, so yeah, we can try to discuss these answers a little bit. So if the matrix would not be square, it would mean we would have more or less equations than unknowns. This would not make too much sense for our equation system and for our solution. So it should always be square. If we want to solve this equation system, then we have to invert it. So if it's a singular matrix, then we could not invert it. Then we would also not get the solution. So this must also be correct. And if it's properly set up, let's say the coupling from node 1 to node 2 is the same as from node 2 to node 1. So there's some kind of reciprocity, let's say, inside this matrix. So that's why it's always also symmetrical to the main diagonal. Yeah, so it must be quadratic, it must be invertible, it should also be symmetrical, otherwise it does not work. And so the the example that we have looked at also fulfills all these conditions. Okay, and so then there's the last question. I've used this straw poll because it is the easiest to set up, but unfortunately every question gets a new QR code. So the question here is, what is the main advantage of nodal voltage analysis over the branch current analysis? So if we would compare these two methods that we have looked at today, what is the advantage? And then we can maybe also shortly discuss what is the disadvantage. Okay, so we have some more votes for the answer options 2 and 3. Now we have we have the same number for each and everything. This is also great. Okay. Okay. So I would say every linear system of equations that you have, you can always solve using matrix calculation. So and we have, remember what we have just done half an hour ago. So also for this branch current analysis, I've set up a matrix. I've solved this equation system in Octave. So this is no genuine advantage of nodal voltage analysis. Okay, the system or the equation system for nodal voltage analysis is smaller, has fewer equations, fewer unknowns. Yes, because we only set up Kirchhoff's current laws and then somehow insert the voltage laws there. That's why we only have, in this case, for our example circuit before, we had 6 unknowns. And an equation system with 6 unknowns can be quite hard to solve. And now we had only 3 unknowns. 3 unknowns is something that you could still solve by hand. The thing is, if you discuss this with computer science people, then they say, yeah, the advantage is not really so strong because the matrix that you have here, so if I output the matrix that we had before, so why do I don't see any prompt anymore? Ah, there it is. So if I output the matrix, this was the branch current matrix, and this was the nodal matrix. This was the old one, and this was the new one. So if you compare these matrices, so this is 6 by 6, this is 3 by 3, 3 by 3, but this contains lots of zeros. And this is a sparse matrix, as computer science people would say, or mathematicians would say, and this is a dense matrix. And so at the end, if you have to solve an equation system from a sparse matrix, it's kind of the same effort as if you have a smaller one, but that has a dense matrix. So yeah, for humans, this might be some advantage. For a computer, it does not really matter. Okay. And this here, the last one, this is the main advantage. You don't need to find this independent mesh equations, for example, using this complete tree method or some other method. In nodal voltage analysis, we start with the Kirchhoff's current laws, and if there are k nodes, there are k minus 1 independent nodes, and the minus 1 is thrown away by setting this reference node. And so it's very simple. Also to program, if you're good at programming, you need maybe, depending what programming language you use, but you need not more than, let's say, 100 lines of code to program a simple circuit simulator that can simulate any circuit with current sources and resistors in any structure. So it's very easy to program this, and that's why this nodal voltage analysis is used. Yeah, so answer 1 is incorrect and the other 2 are correct, but the answer 3, this is the main advantage. This is why everyone uses nodal voltage analysis.